Just hold for 1 second, Ajay. Just hold for 1 second. Yes,
Okay.
yes. You can start now. Okay, I'm totally ready.
Okay then.
Recording. Okay, recording. Who will make a recording?
Yes, thank you.
So Pavel, can we start?
Yes,
Right.
yes, you can start now. Yes.
With kind permission from our speakers, let us start the schedule. On behalf of the organizing committee of the webinar entitled Algebra Analysis Topology, me, Ajay Mukherjee speaking. Welcome back and good evening to all according to Indian Standard Time. Before beginning today's session, here is information on our feedback form. We assure all that we will send feedback form to all at the registered emails within 1 or 2 days of the completion of our webinar. Thank you. Today, we have the privilege to have Professor Anand Prakash Singh and Professor INDRANATH SENGUPTA among us as the honorable speakers. I welcome both of you, sir, on behalf of the Department of Mathematics, Bankura University. Now, I would like to introduce Professor Anand Prakash Singh, the first speaker of today's session. Professor Anand Prakash Singh is currently acting as a professor, head and dean of the schools of mathematics, statistics, computational sciences of Central University of Rajasthan. He is the honorable vice chancellor in charge of the Central University of Rajasthan. Professor Singh is a former professor, head and dean of Faculty of Mathematical Sciences of the University of Jammu. He obtained his PhD from the University of Missouri, Kansas City, USA. He was associated with Imperial College London, UK as a postdoctoral fellow and with Kyoto University, Japan as a JSPS fellow. He visited many countries for short as well as long-term position. Some among such countries are USA, UK, Germany, France, Russia, Australia, Spain, Italy, China, Turkey, Taiwan, Armenia, etc. His thrust area of specializations are complex dynamics, complex analysis, value distribution theory, factorization theory of entire and meromorphic functions. Professor Singh so far guided several students for their PhD and MPhil degrees and published over 75 research papers in national and international journals of repute. In his academic career, he has bagged many awards and honors. Some of his remarkable awards and honors are Lifetime Achievement Award by Forum of Interdisciplinary Mathematics, December 2016, Academic Secretary of Ramanujan Mathematical Secretary 2016 to 2018, President of Vigyana Parishad of India 2014 to 2016, Vice President of Vigyana Parishad of India 2007 to 2013, 13 Distinguished Service Award of Vigyana Parishad of India, March 2011, Member of the Council of Indian Mathematical Society 2006 to 2008, President of Jammu Mathematical Society 1999 to 2001, and second term from 2003 to 2005, Executive Editor for Bulletin of Pure and Applied Mathematics. Apart from several plenary invited talks and paper presented, his some appreciable awards, lectures delivered on various occasions, Platinum Jubilee Lecture at the Indian Science Congress held at Tiruvhananthapuram 2010, Hansraj Gupta Memorial Lecture Award 2004 of the Indian Mathematical Society, Jodhpur 2004, Professor C.S. Venkataraman Endowment Memorial Lecture at 16th Annual Conference of Ramanujan Mathematical Society, Pune 2001. His title of talk is The Mindset of Transcendental Entire Function. Professor Singh, over to you, please.
Okay, thank you. I will try to see whether, can this be seen now?
Yes, yes. Your connection is much more stable, I think, now.
Okay. Well, I thank Professor Mukherjee, Pavel, and in fact, all the faculty members of Bankura University for giving me this opportunity to present my talk. The title of my talk is going to be Bunge Sets of Transcendental Entire Functions. It's a recent topic that I started. It's a little interesting in the sense that maybe it was there, but people didn't do much on it. But only recently, work has started on this topic. So for that, we first go to something more than that.
Sir, are you opening your presentation or?
Yeah, I'm starting.
Okay, okay,
so,
sir. Okay, okay.
Can you see it? Is it clear?
No, sir. No, sir.
You can't see?
No, sir. There is no presentation. We can see your face.
Oh, 1 minute. Then no.
You should hit the present now option.
Okay, yeah. Okay, 1 minute. Yes. Yeah. Okay. 1 second. That was it. 1 second. It was. Recording is there. Present now. Okay. Yeah. Your entire screen. Now, can it be seen?
Yes, sir. Yes, sir. It is very clear.
Okay. Okay, then let me go back. Yeah. So now this is okay. Can be seen?
Sir, yes.
Okay.
Yeah. It's okay. Fine then. So the topic, the title is Bunge Sets of Transcendental Entire Functions. It's basically something to do with the composition of entire functions. Some of you, in fact, must be knowing about the Fatou sets and the Julia sets, and that is where all this starts off. But a little of it I'll have to give so that we can come to it later on. So let f from C to C be rational or transcendental entire functions. For n in n, Fn will denote the nth iterate of f. That is, we are talking about F, composition F, and so on. So Fn of Z is nothing but F of Fn minus 1 of Z, where F naught of Z will be Z. N is equal to 1, 2, and so on. The set, Fatou set of F is well known, is set of all Z such that the family Fn is normal in some neighborhood of Z and is called as the Fatou set. And by normal we mean that it contains all the sequence that we take, it must contain a convergent sequence. Every sequence must have a convergent subsequence in it. So that is your Fatou set, and the corresponding quantity, the complement of it, is denoted by the Julia set. And denoted by JF is called as the Julia set of F. So basically, if you observe, the complex plane is divided into two because it's a complement. So your complex plane has been divided into two parts, that is the Fatou set and the Julia set. There are only two partitions of the complex plane. But now the question, in fact, is, the result is that is it possible to divide the complex plane into more than two different parts? And that is what is being done, as we shall be talking about. Observe that C cap or C union infinity, the extended complex plane, has been partitioned into two different classes of sets, namely the Fatou set and the Julia set, with infinity always taken in the Julia set when f is transcendental entire function. There are other ways also in which C hat can be partitioned, which is also linked with the Fatou and the Julia sets. That means there are other ways also we can partition it, and those quantities are also connected with Fatou set and Julia set. And as we shall go along, we shall see that it is possible. That is, we will be trying to define by a different procedure these quantities, the partitions. Now, in fact, in 1989, Eremenko defined the following. For a transcendental entire function, the escaping set is defined as set of all z such that f and z tends to infinity as n tends to infinity. In fact, this was a problem by Fatou long time back. He considered some functions and asked whether a general statement is true, whether the curves tend to infinity, or do there exist curves which tend to infinity. And this was studied in earnest by Eremenko in 1989, and he defined the term I of f, a set of all z in C, so that f and z tends to infinity as n tends to infinity. Of course, he didn't give a name at that time, but as it was seen later on, became important. So a special name was given, that is the escaping set. That is the points which escape to infinity, the escaping set. So he defined it, and look at the interesting parts of this. He proved that IF intersection JF is non-empty. That means in J of F, in the Julia set of F, there are points which tend to infinity. In the Julia set of F, there are points which tend to infinity in the iteration. F and Z tends to infinity. And not only that, the interesting part is that the boundary of that escaping set is the Julia set of F. So you can see that now with this property, one can study the Julia set. One was earlier using the normal families, but now you could study the Julia set using the boundary of the escaping set. So a new way of studying the escaping set, the Julia set, using the boundary of the escaping set. The boundary of IF is J of F. And then also he also proved that all the components of IF bar are unbounded. That means every component that I consider of IF, they are going to be unbounded, taking with the closure. And he conjectured, and he thought that this bar is not necessary, and he conjectured that all the components of IF are unbounded. He was able to prove with IF bar, but he conjectured that all the components of IF must be unbounded. And this has led to a lot of development in the field. People have been trying, and to date, the answer is still not known. So this conjecture, though not yet solved, has given rise to a rich development in the field. And still the result is not known. Of course, in many cases, it is seen that the components of IF are unbounded. So it looks that this may be true. And if it is not true, the example that you are going to get must be definitely a complicated one. So at least that much is known, that most of the problems that they've obtained, they justify this, but the general answer is still unknown. So this conjecture, though not yet solved, has given rise to a rich development in the field. Now, naturally, if the point is tending to infinity, when I say the point is tending to infinity, we always mean in terms of iteration, z, fz, f2z, f3z, and so on. So now if a point is tending to infinity, say this point here is tending to infinity, and so on, it may happen that it tends to infinity at a slow speed, or it tends to infinity at a fast speed. And that has been studied. So the points which tend to infinity with different speeds, such as fast escaping set, slow escaping points, or relatively fast escaping points, etc., have been studied by various authors. So people have started working in that direction. A subset of IF. So let's give some idea about what we mean by all these quantities. No doubt the points are tending to infinity, but the speed is also an important factor. So let's see what that factor is. So a subset of IF denoted by I naught of F, in which the iterations of a transcendental entire function tend to infinity relatively fast, was considered by Bergweiler and Hinkanen in 1999. And they defined this relatively fast escaping set as set of all z in IF, so that log fn plus 1 of z over log fn z tends to infinity as n tends to infinity. Observe here, it is the gap fn plus 1 and fn. So it is basically the gap that we have here is tending to infinity. So in short, if the point is moving from here, it goes up here, then the gap increases, and the gap increases, and the gap increases. So that is what we are talking about. So obviously they are tending to infinity with the gaps becoming larger and larger. And they not only defined it, they used this result to prove some result. In fact, this was one of the results that proved, there are several that they proved. I've just given one of them to illustrate that they are just not defined just for the sake of defining, but they have relevance also. So they prove the following by Bergweiler and Hinkanen in the same paper of 1999, that let f be a non-constant and non-linear entire function, and g be an analytic self-map of c minus 0. Suppose e raised to f is g of e raised to z. Let this be true. Suppose e raised to fz is g of e raised to z. Then z is in the Julia set of f if and only if e raised to z is in the Julia set of g. So that was the result. They proved that these two are interrelated. And observe that this Fatou set and the Julia set that you are getting here are basically related with the fast escaping set, and that is basically connected with your boundary of the escaping sets. So they prove that Z is in the Julia set of F if and only if e raised to Z is in the Julia set of G. Then Ripon and Stellard in 2010 defined another type of a escaping set. They called it as zipping to infinity. That is, Z of F is set of all Z in IF, so that log plus fn of Z over n tends to infinity as n tends to infinity. So this time they have not compared the gap, rather they have compared it with the nth iterate. So fn as n tends to infinity, fn Z over n with log. So log plus is, that means either this value or its value is 0, which is never negative. If this quantity is 0, the quantity is again taken as 0. So log plus fn of Z over n as n tends to infinity. And the subset of IF in which the iterates of a transcendental entire function tend to infinity was again considered by Bergweiler and Hinkanen. They defined A of F, a set of all Z in C, so that there exists an L, so that fn of Z is bigger than MR fn minus L of Z for n bigger than L, where MRF is maximum of mod fz, Z equal to R, and R is any value such that R is bigger than minimum of Z in Julia set of F. Now just let me give some thought over this particular definition. What it basically says that R is sufficiently large. Why we have taken it? It is bigger than minimum of Z in Julia set of F, because the moment Z is here, there is a theorem of which says the expanding property in the neighborhood of a Julia point, that is, under iteration, the quantities becomes larger and larger, tends to infinity. So we have taken R sufficiently large to include at least one point, so the iteration becomes larger and larger, so that this quantity becomes larger and larger, tends to infinity in terms of the modulus. And not only that, what we are basically saying is that this particular quantity, what we are saying here is that this particular quantity is bigger than MR fn minus 1. There is an L exists. 1 second, just one. Can you hold one minute? Let me just see if I can do something else. Basically, what it says is we are having some region, and it is becoming larger and larger because there is a point in the Julia set here. So when I take the image of it becomes bigger and bigger. and so on. It becomes bigger and bigger. Now it is those points, there are some points, let's say some point here. When I apply F on it, this moves up somewhere here. And if I take, let's say, this unit circle here, if this quantity under iteration, the maximum modulus of this is some quantity, let's say the maximum modulus of this gives us this quantity, say somewhere here. In one stage, this quantity moves up somewhere here. In the second stage, MRF comes up here. At that time, this point moves up somewhere here. And the next, the MRF of this, the third stage, is somewhere here. This moves up. Or in other words, the quantity that we are talking about here is always outside these MRFs after a certain stage. Maybe even it may be a point somewhere here. This original point, of course, the very first quantity may come up here. But if the point is such that it moves up somewhere here, maybe after 2 stages, it is somewhere here. Now, after 2 stages, the next stage is here. This point has moved away. The next stage is here. The point has moved away. So such points will be said to be present here in this. So there exists an L in it so that this Fnth iterate is always bigger than MR Fn minus 1. For example, F5 will be bigger than MR of F3 if this is your 2, so F3. M6 will be bigger than M4, MR4, and so on. So naturally this is tending to infinity, and this is always outside it. So they are obviously elements of your escaping set I of F, a special type. You can say they are tending to infinity at a fast rate, where MRF is, as usual, maximum mod F set. Now, this definition of AF was used by Bankura and Nikera. In the same paper, they gave 2 different terms. The following: let F and G be translated entire functions with F composition G is equal to G composition F. Further, let both F and G have no wandering domains. Then the Julia set of F is the Julia set of G. So observe that this was an important result. In fact, let me again point out here that for rational functions, that is, if F and G are rational functions, then it is known that F composition G is and G composition F, they are equal. Then both the Julia set of F is equal to Julia set of G. So that is a well-known result. But for transcendental entire function, the result is still open. Still, the complete answer is still not known. Of course, a lot of work has been done, but the complete answer is not known. And observe that this escaping set that they defined give at least a partial answer to that. That is, if F and G are entire functions and both have no wandering domain, if they have no wandering domain, then the Julia sets of F is equal to Julia set of C. So that the general problem that is now left open is if both of F and G have wandering domains, then what happens? If they have one, or one of them has a wandering domain, then what happens? So that is still left, but at least a part of it has been proved using this escaping set of this type. And in fact, this is what I have mentioned here. It is well known that if F and G are rational functions, with F composition G is equal to G composition F, then the Julia set of F is Julia set of G. And this actually follows because of the Lipschitz condition that is true for rationals, but it is not true for transcendental entire function. That's why this technique cannot be used. So if F and G are transcendental entire functions with F composition G is equal to G composition F, then is the Julia set of F is equal to Julia set of G? This is still an open question. Of course, the part, as we just seen, has been proved. There are other parts also that have been proved using these escaping sets. So let's move ahead. And the subset of IF, by the way, I hope I'm clear, audible.
Yes, sir. Yes, sir. You're completely
okay. It's audible, okay. And it can be seen. The slides are clear.
Yes, sir. Completely.
Okay, then, yeah. Okay, and the subset of IF. Now, we are talking about these escaping sets. So, and the subset of the escaping set in which the traits of a transcendental function tend to infinity arbitrarily fast was considered by Ripon and Stallard, and they defined A of F, set of all Z in C, so that there exists an L in N, so that Fn L of Z is bigger than Mn of Rf for N bigger than L, where again MRF is maximum of this, Mn Rf is this time the iteration, that is M of Rf, and then the next again M of quantity, so iteration we are talking about, denotes the iteration of MRF with respect to the variable R, or equivalently when MR and F tends to infinity, because we have taken this bigger, so the quantities are tending to infinity. Now this is slightly faster than the earlier one. Here we are taking Mn of Rf. Earlier we had taken this term. Fz is bigger than Mr, Fn minus 1L here. In the next one, the one that we just showed, the N is here at this stage, not here, but here. So maximum modulus iteration. Here we are talking the function iteration. Yes, obviously the maximum modulus iteration is faster. So if that is faster, that will always imply this quantity. So the iteration here. And using this, they call it arbitrarily fast. And using this, they proved these three results. That AF is non-empty. That means the fast escaping points, they always exist. For a transcendental entire function, the fast escaping points will always exist. And in this case also, just as earlier, we had that Julia set of F was boundary of IF. Even the boundary of these fast escaping points is the Julia set of F. So observe, this gives a lot more information than the earlier one. Earlier said the boundary of IF, and here is a subset that we are talking. Even this subset that we are talking about is going to be Julia set of F. And again, AF intersection Julia set of F is non-empty. That means there are points in the Julia set of F which tends to infinity at a very fast rate, at arbitrarily fast. That is at this property. Now using this fast escaping set, Ripon, Benini, Ripon, and Stallard proved the following. Let F and G be transcendental entire functions with F composition G is equal to G composition F. Further, let both F and G have no simply connected fast escaping set. Then the Julia set of F is Julia set of G. Now once again you observe some more progress has been done using these results. In fact, here the proof I have not given or mentioned here. It was given by them. Again, they used the previous fast escaping set. Using this concept of fast escaping set, they proved that in this case, if the functions have no simply connected fast escaping wandering domain, then the Julia set of F is Julia set of G. Observe, the first result was if there are no wandering domain, the result is over. Now, in this they have said if there are no simply connected fast wandering domain, then they are equal. So the question that still remains open is if they have simply connected fast escaping wandering domain, is this true? That is still an open question. The progress is being made, and all the progress corresponding to this has been obtained using these escaping sets. Now, defining this, if you go back, we mentioned here, there exists an L such that this condition is true. There exists an L, some number, so that this condition is true. In that case, we study the arbitrary fast escaping set. They later on, Ripon and Stallard again looked at it. Why not study this part, this L, instead of studying that there exists? Why not study that individual L which satisfies this? And that is called as the Lth derivative. I mean, Lth escaping set. So this L that we talk about, and then study the property of this L corresponding to that function and see what is the relation between these. And that is what is done here. Let F be a transcendental entire function and let L be in Z and let R be bigger than 0 MRF is bigger than R and R greater than equal to R. Of course, all this is just to make sure that the values become larger and larger. The quantity that we talk about becomes larger and larger, the area. The Lth level of A with respect to R is given by set of all Z, set f and Z is greater than equal to Mn plus L of Rf for n and n plus L in n. So this is how they define the Lth level. Earlier, we mentioned that there exists an Lth level. Now we are defining the Lth level by that quantity. And this Lth level that we are talking about has certain properties. So they are again, they're proved by them. So I just mentioned it for you to get an idea. That A R naught F is denoted by, that is 0th level, is denoted by ARF. And then, of course, there are relations between Lth level and L plus 1th level. They lie between these. F of ARL F is subset of ARL plus 1 of F, is subset of ARL F. And the total fast escaping sets that we define there exist. All this total A of F is nothing but AR minus L, n is equal to L belonging to n. So we can study the union of all these levels would give you the corresponding A of F. And it's known that A of F is a closed set. AF is a closed set, but it's interesting that ARL need not be closed. This individual, the Lth level may not be, but the total level, of course, is closed. So AF is closed, but the Lth level need not be closed. Also, each component of AF is unbounded. Using this level, they prove that each component of AF is unbounded, every component. So in particular, IF contains at least one unbounded component. So this IF contains at least one unbounded component, namely AF. So a partial result confirmation of the result of Eremenko. He mentioned that IF contains every component is unbounded, but here at least one of them, namely that AF is unbounded. Next, let F be transient entire function and n be in n. If n is sufficiently large, they also showed Ripon and Stella proved that the 0th level that we are talking about here, the ARF is subset of ARF and is subset of AR by 2F. So that is the relation between the levels that we talk about, the 0th level for the function and its iteration. We proved, that's myself and one of my students, Garima Tomar, we proved the following, that instead of this, we tried to generalize it up and we show that AR NLF is subset of AR FL is subset of AR2 by 2 NLF. And obviously, we have the second one also. There's nothing special about it. It's exactly almost the same. Because, is it okay? Hello? Yeah.
Yes, sir. Audible.
Okay. Audible. Okay.
Okay.
So,
okay.
Fine. So here we had the same NL is there. So n times L, whether I write L times n or n times L, it is the same. The proof, there is not much of a difference. So from that point of view, proving one is this immediate, the second is immediate. But the interesting part is that no doubt they are equal, but these quantities that we are having here may be different. So interesting observation of the above theorem was that if P is a composite number having two different factorizations, say P is equal to P1 Q1 and P2 Q2, then we'll have APR as P1 Q1. Remember, it is nothing but NL is nothing but n times L or L times n, they are the same. So from that point of view, there's nothing much of a difference. But this is the interesting part, that if they have two different factorizations, then AR P1 Q1 and AR P2 Q2 will also lie, and these may be different. So note that these quantities need not be equal. Now, Ripon and Stellar observed that this AF and also the 0th level have interesting and intricate structures called infinite spider's web, which was defined as follows. They defined it as a set E is an infinite spider's web if E is connected and there exists a sequence of bounded, simply connected domains, Gn and Nn, with Gn subset of Gn plus 1 for n in n, and boundary of Gn is E for n in n, and union of Gn is C. So in fact, the definition they have taken is most reasonable. It's like your usual spider's web. These corresponding strands coming up and so on. It's infinite, it doesn't stop. And let's see whether this diagram that is on this side and all that, it goes up to C. So let us see whether it satisfies all the conditions, the spider's web. A set E is an infinite spider's web if E is connected. Look at the red lines, all these are connected quantities. All these are connected. E is connected, and there should exist a sequence of bounded, simply connected domains Gn with G1 subset of G2. I take G1 region as this much, G2 as a still bigger one, the two of them from here to here, that is this much is your G2. G3 is still bigger, containing these two and then the 3 and so on. G4 would be these 3 union one more, G4 and so on. So we have Gn is subset of Gn plus 1, that is G1 is subset of G2 is a subset of G3, G1 is subset of G2 is subset of G3 and so on. Boundary of Gn is a subset of E, boundary of G1, boundary of G2, boundary of G1 is a subset of E, boundary of G2 is this much, there's again a subset of E, boundary of G3 is this portion, there's again a subset of E and so on. So boundary of Gn is a subset of E for n in n, and the union of Gn, union of this G1 union G2 union G3 and so on is the whole of C. So this is how we define as infinite spider's web. Why this term is the following. Riemann-Stieltjes, they prove the following. For sufficiently large R, if the zeroth component AR of F complement has a bounded component, the fast escaping set we are talking about, has a bounded component, then each of AR, F, AF, IF is a spider's web. And so if the complement portion, intuitively, if you can get an idea, if these quantities are bounded, then the complement is going to be these lines, and that is going to form a spider's web. So all of these form spider's web. IF also forms a spider. And for n in n, ARF is a spider's web if and only if ARFM is a spider's web. So the spider's web do play part in our escaping sets. They also consider the following. There are several other properties of spider's web. Just to give an idea, let F be a transentire function and let R be bigger than 0, so that MRF is bigger than R, R greater than R. Then ARF is a spider's web. This will form a spider's web if one of the following holds. F has a multiply connected Fatou component, or F has a very small growth. That is if log MRF over log R over log MR, that is your iteration. Log of etc. M of R. This quantity is less than that, then your F has, then your ARF is going to be a spider's web. Or if F has a order less than half and regular growth, that means lower order and upper order are equal but less than half, then also ARF is a spider's web. So there are several examples that exist, are known. I think I'll be skipping these. Okay. So, and we proved for that the following, that F is an entire function, let R be bigger than 0 such that the conditions are true. Then AR and LF is a spider's web if and only if AR and FL is a spider's web. So the corresponding to F, a spider's web, I can come to FL also as a spider's web. Note that intersection of two spider's web need not be a spider's web, because naturally the intersection will be the points. When you take two intersection of two spider's web, if I take another spider's web, the intersection that I get is going to be points. So intersection of two spider's web need not be a spider's web, but the union is going to be. Let SI be spider's web, then the union of SI is also a spider's web. Of course, We don't know whether the arbitrary union of spider's web is a spider's web. At least finite is okay, but arbitrary union, we still don't know whether that is true or not. Because it may turn out to be the whole of C, and whether that works or not, many other problems do come up. So we don't know that quantity. So all these results, again, myself and the student. So a continuous image of a spider's web need not be a spider's web. Because if I take a constant function, for example, it is a small piece, and it is, naturally it cannot extend to infinity, so it cannot be a spider's web. But for a spider's web, the strands must tend to infinity. So continuous image of a spider's web need not be form a spider's web. For instance, a constant function does not yield a spider's web. However, images of continuous function under certain conditions, just this is not sufficient, but some extra conditions may yield a spider's web. And we have proved the following. Let F from C to C be an open, continuous, and surjective map. Further, let F map every bounded domain to a bounded domain. If S is a spider's web, then the image F of S is also going to be a spider's web. And as applications, we also prove the following. If F is a transient entire function with no finite asymptotic values and no exceptional values Picard, then F is a spider's web. If F is a spider's web, then so is F of S. So F of S is also a spider's web. Now, till now here, what we have considered were the points which are tending to infinity. Now, there are points which do not tend to infinity. So, in contrast, there are points whose iterations under F remain bounded. The set of such points is denoted by K of F and is defined by the following. K of F is set of all Z such that there exists an R bigger than 0, so that all the iterates lie within this circle of radius R, center 0 and radius R. All F and Z are this quantity. So it is bounded inside it. Now, for a nonlinear polynomial P, K of P is known as the filled Julia set, which has been extensively studied by several others. We will not go in that direction. Our direction is slightly different. So, for transient entire function, Kf has been also studied, for instance, by Burgweiler and Osborne. That is the bounded set, points which do not tend to infinity. So earlier till here, we considered the points which are tending to infinity. Here we have considered the points which do not tend to infinity, that is, they are bounded. So now the question is, what can we say about the other portion? Now, Osborne in 2016, 2016, consider the following. For a transient entire function, the Bunge set is defined by B of F is equal to set of all C minus I. That is the points which are neither bounded nor tending to infinity. And these have been studied. They are called as the Bunge set. And that is the topic that we want to work on. So let me give an idea. What do you mean by a Bunge set? A point which is neither bounded nor unbounded. Let's look at it. It may be some point, say here. It after one iteration, two iteration, it comes outside. And then after some, maybe after that, it comes inside. Then again, it goes out. The number of iterations may be different. Number of maybe of 2 or 3 steps, it comes in again. Again, after some, it remains in, but then again it goes out, and then again comes in. So observe that this point that we are talking about here is neither bounded in iteration because it is tending to infinity. It is not tending. It is unbounded in. It is not tending to infinity in that sense because ultimately there are after a certain stage it comes in. So it is neither bounded nor unbounded. So such points have been studied. They are called as the Bunge points. So they keep going in and out. So that is what I mean. And of course, you can observe that if this is a Bunge point, then obviously this is also a Bunge point, which is a Bunge point. So in fact, if there is at least one, your Bunge set all these is always going to be an infinite set. So this is what for a transcendental function, the Bungee set B of f is defined by set B of f, Bungee set of f, a set of all that is the C minus the points which are not bounded, and at the same time they are not tending to infinity. So now if you observe, your complex plane has been divided into three parts, 1, 2, and the third one here. Earlier it was Fatou set and the Julia set in 2 pieces, but now we are having it in 3 different pieces: the Bungee set, the bounded set, and the quantities which are tending to infinity. Now, some simple properties of Bungee sets are the following. As each of IF and KF are completely invariant, it follows that Bungee set is completely invariant, because this part, this IF is completely invariant. The bounded part is also, the KF is also completely invariant. So obviously, Bungee set is also completely invariant. So, and IF, KF, and BOF partition the complex plane C in 3 classes. All are disjoint. They are partitioning, they are disjoint. Now, instead of using this notation as a complement and then working it out, we have defined it, the Bungee set, using another terminology, the same thing, but in a different way that we have used in our paper, and it's here. We define the Bungee set as a set of all Z that there exist at least 2 subsequences fnk and fmk with nk tending to infinity and mk tending to infinity as k tends to infinity, and a constant r bigger than 0, so that fnk of z is less than or equal to r for k equal to 1, 2, and so on, and fmk of z tends to infinity as mk tends to infinity. So that means in Bungee set are those points for which there exist 2 sequences, fnk and fmk. So if you go back, we had this quantity. For example, if I consider this particular point, this may be in the Bungee set, because I can find a sequence 2 goes outside the circle, then 3, F2 goes outside, F4 goes outside, F5 is outside, and then 8, 9. F10 is outside, F11 is outside, and so on. And then there is again F3 which is inside, and maybe some other quantity which is inside. So there are some iterations which are inside, some iterations which go outside, and in the same iteration that we are talking about, 2 subsequences, one remaining inside it and the other going outside, tending to infinity. Okay. So there exist at least 2 subsequences, fnk and this quantity with nk tending to infinity and nk tending to infinity, so that one of them is less than or equal to r and the other tends to infinity. Now these 2 subsequences cannot have a pattern, in the sense that for a point z0 in f, I cannot find 2 sequences nk and mk such that nk is k times n0 and mk is the same k times n0, where n0 and m0 are bigger than 1, k is equal to 1, 2, and so on, so that fnk is less than or equal to r and the other one, fmk, is tending to infinity. So what basically we are saying is, look at the structure. What I'm trying to say is there is no regularity. We shall keep this in mind, that our nks, just to be consistent, there are 2 nks that I take. Yeah, nks that I take will be less than or equal to r, bounded side. Mks will be tending to infinity. The first nks bounded, the mks tending to infinity. That will help us in many places to get an idea. So keep this in mind. Nks bounded, mks tending to infinity. Here we are saying the nks that we are talking about is like having some fixed number. So n naught, then 2n naught, 3n naught, 4n naught, 5n naught, in that order. Similarly here, m naught, 2m naught, 3m naught, 4m naught, so that a pattern that we are talking about is not possible. Let's try to give, it's a simple proof. Let's try to look at it. Suppose they do exist. Choose k sufficiently large, say L, so that fmk of is bigger than R. Mk's are tending to infinity, so I can choose it bigger than R. So, naturally, but by definition, mk is nothing but f k m naught of z naught is bigger than R for all k bigger than L. And in particular, I take still bigger numbers. I take k m naught n naught, because there's still a bigger number. It is true for all k after that, for all k's after L. So if I take k n naught bigger than L, this statement will definitely be true. But then I combine this k n naught as nk, so I get, so we combine this k m naught as some t, so we have t n naught. But remember, the n naught were bounded, so this of course is fn of t is bounded. So on this side we are getting bounded, the other was tending to infinity, and so because here we said these quantities were tending to infinity, bigger than R. Here we are talking about something, the same term, bounded, so it is not possible. So that's there. Now for a nonlinear polynomial, the Bungee set of P is always an empty set, because everything will tend to infinity, so nothing like moving like this. So that's always true. And for a Church-Link entire function, Bungee set intersection Julia set, all these are known results. That Bungee set of F intersection Julia set is non-empty. That means Julia set of F will always contain Bungee set points. And Bungee set of F intersection Fatu set is also non-empty. There are examples, not always, but there are examples where this quantity is non-empty. In fact, Sixsmith proved that if F is Church entire function, then every component of Bungee set of F must meet Julia set of F. Here we have said it is non-empty, but later he proves that even the every component will intersect. Here is just one of them maybe, but that is easy to prove. Then here he has proved that every component of Bungee set must meet Julia set of F. Pavel, how much time do I have still?
Sir, you can continue for 10 minutes.
10 minutes, okay. Okay. So let Fz be, so here are some more results that are known, just to give an idea, that Bungee set of F is interesting in the sense that there are examples of with the different natures, that the type of Bungee sets one can expect. For let Fz be lambda e raised to z for lambda in 0 1 by e, then the Bungee set of F is totally disconnected. So there exist examples where the Bungee set is totally disconnected. There are examples here has uncountably many unbounded components, and each with empty interior. For this, excuse me. And then there exists Church entire function F, that the Bungee set of F contains no unbounded Fatu component. That means the components are all, Fatu components are all bounded. So some work has been going on the Bungee sets. Now for rational functions, the Bungee set may coincide with the Fatu set. Of course, in general it may not, but in this here, for rational functions, the Bungee set may coincide with a Fatu set. For example, if I take 1 by z square, then the Bungee set of R is mod z less than 1 union mod z bigger than 1, and Julia set of R is nothing but boundary of Bungee set of R. Again, if you are talking about the 1 by z square, if I have the unit circle, I'm talking about 1 over z square function. 1 over z square. So when I take a value the next iteration will give you z to the power of 4. So half would go to 4, and then 4 would give 1 over 16 inside, and then outside, and so on. Anything that I start will move like this. So every point here is a Bungee point because it keeps on going. Similarly, every point here is a Bungee point. Only the points that, of course, remain are here. And you know that the Julia set of this is this portion. So the boundary of the Bungee set, namely this union this, that's your Bungee set. The boundary is going to be this Julia set. So for 1 over z square, Bungee set of R is mod z less than 1 union mod z bigger than 2, and the boundary of the Bungee set is going to be Julia set of R. It is interesting to note that if R and S are permutable rational functions, then R composition S is S composition R. That is well known, as we mentioned. For transcendental, most of the results are known. In fact, in most cases, we obtain that they are equal, but the complete result is not yet known. But if I talk about rational function, the Bungee sets for rationals is not true. However, the corresponding result for a Bungee set is not true. Here, if R composition S is S composition R, then JR is the same as JS. Now look at it. RZ is this quantity. Let's take SZ as this quantity. Then R composition S is S composition R. They are equal. R composition S, 1 over z to the power of 4, and the other is also 1 over z to the power of 4. But the Bungee set of R, as we just seen, is this quantity, whereas the Bungee set of this is an empty set. So this type of relation need not hold true for a Bungee set, though it's true for Julia sets. That the Bungee set may behave quite differently from the Julia sets for rational functions and transcendental entire functions. It is also well known that for any n, Julia set of Fn is the same as Julia set of F, and Fatu set of Fn is the same as Fatu set of F. However, this is not true for Bungee sets. Okay, the same example will work. We only have one set, that is Bungee set of Rn is subset of Bungee set of R. Since for instance, just to give an idea, let's take Rz as 1 by z square, and then Bungee set of R square would be z to the power of 4, reciprocal of the reciprocal z to the power of 4, is an empty set. Bungee set of the z to the power of 4 function is an empty set, whereas Bungee set of R, of this we have just seen, is this portion. So Bungee set of R and Bungee set of R square are different, whereas here, for the Julia sets and the Fatu sets, they are same. So they behave differently. Now let F be a transcendental entire function. If W is a Fatu component of F and W intersection Bungee set is non-empty, then the following is the result that they proved. That if W will be in Bungee set of F and W is a wandering domain. Or in short, if the moment there are points of Bungee set in the Fatu set, W is a Fatu component of F. So Bungee points are present in the Fatu set. If Bungee points are present in the Fatu set, then the boundary of the Bungee set must be the Julia set of F. If there are points from this Bungee set into Fatu part, then the boundary of the Bungee set must equal to Julia set. And not only that, this W that we are talking about here is a component. It is just not any component, it has to be a wandering component. So if there are points inside here, there are two things. One is that this component, Fatu component, cannot be periodic. It has to be a wandering domain. And not only that, the boundary of the Bungee set is going to be Julia set of F. And as a result, a simple consequence is if F is a transcendental entire function and Bungee set of F intersection Fatu set of F is non-empty, then the Julia set of F coincides with this quantity. Now using this, we proved the following: that F be a transcendental entire function without a wandering domain. then Bungee set of F cannot be a closed subset of C. Question is whether Bungee set can be a closed or open, or what type it is. Because we have already seen that there are different properties we observe. For example, we obtained that Bungee set is at times totally disconnected. We can have uncountably many components and so on. So what else can we say? What about the closed? Is it going to be closed? And the answer is not, at least no, if the function has no bounding domain. So let F be a transient entire function without a bounding domain. If no bounding domains are there, then the Bungee set of F cannot be a closed subset of C. Let's see how. Suppose Bungee set of F is a closed subset of C. Let's assume this quantity. Suppose we shall try to get a contradiction. As Bungee set of F is non-empty, that we already seen, already mentioned, in fact has infinitely many points, it contains infinitely many points because we have all those the corresponding points inside it. Also clearly, Bungee set of F is completely invariant because we already know that IF and the KF are both completely invariant. So the complement BOF is completely invariant. Also, it's well known that the Julia set of F is the smallest closed completely invariant set having at least 3 points. That's the standard result in complex dynamics, that Julia set of F is the smallest closed completely invariant set having at least 3 points. And here our Bungee set, we assume closed. So it is completely invariant, having infinitely many points, and closed. So by that it follows that Julia set of F must be a subset of BU of F. Now, we should suppose if Julia set of F is not equal to BUF, let's see, we'll try to get a contradiction. If Julia set is not BUF, that means to say it is a proper subset. JF is a proper subset. That means there is a point here which belongs to the Fatu set because it's a proper subset. So some Fatu point must be here. So if JF is not equal to BF, then there exists some Z0 in BUF intersection Fatu set of F. And consequently, there exists a component containing F which intersects by the theorem that was mentioned here. If the intersection is non-empty, then W must be here and W must be a wandering domain. At the moment is the point common to Bungee set and Fatu, then W must be a wandering domain. So here, if Z0 is present, then there is a W inside F, and so by which intersects this quantity, and so by the previous theorem, W must be a wandering domain. But this contradicts that the function is having no wandering domain. So it means to say that Julia set of F must equal BUF. So they two must be equal. So JF must equal to this quantity. But then again, if this is true, observe again there is a problem. But then this also is not possible because as rippling periodic points lie here, so rippling periodic points must lie here, but rippling periodic points cannot be a Bungee point because they have to tend to infinity, but it means either bounded, unbounded, 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 it should keep on doing it. Whereas if it's periodic, ultimately it comes and settles down at that point. So it cannot be a Bungee point. As rippling periodic points lie in the Julia set, and periodic points obviously do not lie in the Bungee set. So it means to say all the problem came up by this supposition. So Bungee set of F cannot be a closed set, provided it has no wandering domain. The function has no wandering domain. Then there are other theorems also. If F is transient entire function and P is a bounded periodic domain, then the boundary of P intersection Bungee set is empty. Observe what we are basically trying to say is we are having basically what we are saying is we are having some periodic domain. So naturally, if they are periodic, the quantities will move around and then come back. They will be coming back. All the points will be coming back. The question is, what about this boundary? Theoretically, at least, it may be that these points on the boundary of this periodic component, they may be zigzagging. But the theorem that we have proved is that this is not true. That is, the moment is a periodic component here, your Bunge points cannot be here. They have to be somewhere outside here. Or this is what we say. If f is transcendental function, let P be a bounded periodic component of a set, then the boundary of P intersection the Bunge point is empty. That means on the boundary, we don't have any Bunge point. The proof we are given, I think I will not go into it. We'll be trying to complete. I think I've taken more than sufficient time. The next theorem that we proved is that if f and g are permutable transcendental functions, and let W be in Bunge set of f, if G inverse of W is non-empty, then G inverse of W intersection IF union BUF is non-empty. So again, we are having the functions. We are having your F here, and then G, and here we have some W, which is a Bunge set of F. So I take G inverse of this, G inverse of W here, then this is going to be a Bunge set of the quantity that is on this side. Of course, here I've given a simple proof only for G inverse of W intersection Bunge set union IF is non-empty. That is, even this can be removed out. It takes a little more time. I have not given proof here, but this can be also removed. So we have basically that G inverse of W intersection Bunge set of F is also non-empty. Then, if f is transcendental function, if Z0 is BU of composition, then G of Z0 is going to be a Bunge set of G composition F. Corresponding G moves up to this portion. So again, the proofs of this can be given. There are other theorems. If f and g are transcendental function, okay. If f is transcendental function and Z0 is in, then there exists an R such that the station Nk and Mk exist, such that Fn of Z0 is less than or equal to R, and we denote this domain by mod z less than or equal to R by dr of Z0. Okay, here we had this quantity R. Observe, if I call this quantity as R for the Bunge set, I can also call this portion as also as a corresponding R dash R. There exists an R, so naturally if it works for this, it will work for this as well. And because naturally this much is bounded, and then again they are tending to infinity. Now this type of notation is what we have used here. If f is transcendental function, Z0 is Bunge, then there exists an R, the earlier circle, with these conditions tending to infinity, so that it is less than or equal to R as R tends to. We shall denote such a domain that is mod z less than or equal to by dr of Z0. Note that such a dr of Z0 is not unique. Right? The theorem that we have proved for that is the following. If f and g are permutable transcendental functions and p be a polynomial of degree greater than or equal to 2 and h be a transcendental function such that p composition f is h composition g, and then if Z0 is in BF, then g of dr of Z0 cannot be a periodic domain of f. So this domain, the image of this dr, that disk, will never be periodic domain, no matter how large R I take. So I think I'll skip all that. The proof, I think that's, there are several questions one can work. I think I'm right on time, I guess. So does there exist transcendental function f such that VF is connected? Or is there a transcendental function f with unbounded wandering domain in VF, all of whose iterations are unbounded, or does there exist a transit function in which the bounding domain is in K of F? So these are some of the questions that are still open. One can try. So with this, I think I will be stopping here. So if there are any questions, you're welcome to ask.
Okay. Thank you very much, Professor Singh, for your wonderful enlightening speech. This will surely enhance the research interest among our audience. Now it is time to take questions. I would like to request Dr. Pavel Pal to conduct the question answer session. Over to Dr. Pal, please.
Thank you, Professor Mukherjee, and thank you very much, Professor Singh, for your nice presentation. Very nice presentation, actually. Sir, can you see our Google Meet chat box?
No.
If you click on the
One
right,
minute.
yes, this one. Yeah.
Okay.
I put 4 questions. The first question is from our departmental senior professor, Professor Hajra. Please, can you go through that question?
Yes. Yeah. If the starting point of your iteration is not from a circle or from any convex set, still the iteration will bring the point back to the same convex set. Yeah, we have not put any condition. It was just a diagram that we just showed. Yeah, I just took this just to give an idea. It's not necessary it is here. It could have started from here. Only thing is, there is a disk we can get. There is one disk that we have. So if this point that we have moves up here, goes like this, becomes larger, that is okay. So anywhere it can be. The circle is not an important thing. The only thing is that there exists, it has to come back. There is exist an R with that radius, some radius, so that it is present inside it. So it's not necessary to start from here. It can start from anywhere. So that is there.
Okay. So second question is from one of our speakers.
Yeah. Yeah. Are there any algebraic tools for studying these kinds of questions? For example, does the theory of iteration of monodromic groups have any relevance to these questions? Maybe I don't, frankly, I don't have any idea about the question that we have here, but maybe, because it looks quite interesting, because basically we're trying to iterate and it's basically having two sequences and we're trying to look at the structure. So maybe it may be useful, but I have not tried on this quantity, but maybe it might be possible. And then you have proved partition to of the complex plane. Is there a partition for the same type in plane R2 also? In R2, yeah, it can be done. There's no restriction about that. The only thing is that when you are talking about, you'll have to consider the corresponding convergence of the sequences, and then of course bounded sequences, and still it can be worked there as well. Yeah, it can be worked there also. In fact, it can be worked anywhere. That as long as you have the sequences, one that is bounded, and then of course one that is tending to infinity, and then of course the one which just keeps on oscillating. And Bunge set, as the word itself shows what it means, because if you remember, that's like on your circus net, you keep going up and down, up and down, up and down. That is exactly what the Bunge sets are all about. So you have to keep on going up. That's the thing. Okay. What about Bunge set of R? Yeah. Why is Bunge set of R square empty set? Because when you take R square, we are talking R of R. So it's reciprocal when we talk about is Z to the power of 4. So basically we are talking about the Bunge set corresponding to Z to the power of 4. And the Bunge set corresponding to any polynomial is going to be an empty set, because ultimately everything will tend to infinity. So it won't come back. So it will tend to infinity. So Bunge set is going to be an empty set. And then how infinite ordered entire functions are related to complex dynamics. Well, See, for example, if a function is of, the reason I can give you is the following, that if a function is of finite order, then it has a finite number of asymptotic values. If the function is of order k, it has at most 2k asymptotic values. And if the critical values are also finite, in that case, the function that we are talking about will have no wandering domains. So in order to get something of wandering domains, we may require at times the infinite order. So it is related with that quantity. What is the interpretation of for the entire function of order 0? Interpretation of the entire spider's web for some results are known on this. So order is less than half, so order 0 comes up into that part. So work has been going on. Let me point out that the diagrams for this, there is only one diagram of spider's web that has been drawn by Rippon and Stallard of the spider's web. That is there in that paper that is mentioned there in that index. References that I've given. And the others are theoretical results that we obtained, but exact drawing may not be possible. So,
sir,
yeah.
In your presentation, we see two partitions of C, one in terms of Fatau set and Juliet set, and
right,
involving Bungie set, IF and K.
Yeah.
Sir, you have explained various relationships between
Right.
these two partitions very well. Okay.
Yeah.
So one, I just want to know one example where Bungie set and Fatau set intersection of these two sets is non-empty.
Bungie set and Fatu set.
Fatau set, yes.
I think it must be there. 1 second. If the function has no wandering domain, one minute, let's see that. It must have been there. That. If W is Fatu component of and this is non-empty, then W is a subset of the, and W must be a wandering domain. So this would come up here. If W is a Fatu component, and there is a question of this intersection of a Fatu component, and this will come up when we are talking about a wandering domain. And if you have an idea about it, the wandering domains that we talk about, naturally they are tending to infinity. And so in that case, so if you're having a wandering domain, they keep going in this way, tending to infinity. So naturally, there will be points which will be tending to infinity. And naturally, every point cannot tend to infinity. Every point cannot tend to infinity because otherwise it becomes only one component. So there would be points here which would keep coming back. And when you're talking about, say, multiply connected domains, so always a wandering domain. Then in this portion, it moves up here, and then moves up here and here. Then there would be points which would not move up in this way. So they would come up, they would remain bounded somewhere. So they will exist. So they will be coming up basically when you're talking about wandering domains.
Okay.
So that's where we'll be getting.
Okay, sir. Okay. Thank you. Thank you very much. Thanks a lot, sir. For the limitation of time, we have to end this session right now, actually. Now, please allow us to march forward for our next speech. And also allow me to request Dr. Bappa Das to introduce our next speaker.
I'll stop here. Stop presenting.
Yes, sir. Yes.
Yes, sir. Okay.
And please, Dr. Das, please, can you?
Thank you. Thank you. Okay, for the next speech, please allow me to introduce our next speaker, Dr. Indranath Sengupta. Dr. Indranath Sengupta is very popular name, especially we are from Jadavpur University. He is known to me as ISG sir. Just one word I want to say to ISG sir. Sir, remember me as that Bapadas, we organized a national level seminar at Ramakrishna Mission Vidya Mandira, Belur Moth, Belur Howrah. You was one of the main speaker of that seminar. I was there at that time. I think it was 2016, and many times I have heard and enriched by your lecture. So I now enter his brief bio notes as of my routine work. Dr. Indranath Sengupta did his BSc in 1991 and MSc in 1993 from Jadavpur University. After that, he joined the PhD program of Indian Institute of Science, Bengaluru, and worked under the supervision of Professor Dilip Patil. Dr. Sengupta completed his PhD in the year 2001 and returned to Kolkata to join Jadavpur University as a faculty member of the Department of Mathematics, Jadavpur University. He has served the university till 2014. Currently, Dr. Sengupta holds the faculty position of Associate Professor in Indian Institute of Technology, Gandhinagar. In the meantime, he visited various universities in India and abroad. Some of these are universities of Utah, USA, as the Voicecast postdoctoral fellow of the DST Government of India during 2003 to 2004, University of Missouri, Columbia, USA, as a visiting faculty in 2007, University of Valladolid, Spain, as a visiting scholar with a research fellowship from Spain in the year 2009. Dr. Sengupta has also served at the Ramakrishna Mission Vivekananda University. Now it is known as Ramakrishna Mission Vivekananda Education and Research Institute, shortly RKM Veri, and as a reader during 2008 to 10 on Lane from Jadavpur University from his faculty position. Dr. Sengupta's primary research interest is in commutative algebra and algebraic geometry with an emphasis on the combinatorial and computational aspects of the subjects. Dr. Sengupta takes a keen interest in teaching and also on the pedagogic aspects of teaching and mathematics. He has been associated with various outreach activities for the last several years. The topic of Dr. Sengupta's is some problems in commutative algebra and geometry. So, Dr. Sengupta, please continue your lecture now. Sir.
Can you hear me clearly?
Yes, sir. Audible and visual.
Okay, thank you so much. Thank you for this invitation. Thank you for the introduction. This a two-day international webinar on algebra analysis and topology is being organized really well. A special thanks to the organizing committee, surely to Pavel. And I feel really honored to get a chance to speak here, and especially among respected Professor MEAKIN, Professor ABHIJIT DASGUPTA, Professor SINGH. So It was a little difficult for me to decide exactly what I should be talking on. So what I've tried is that, so let me share my screen, and do let me know if the screen is visible. Can you see the screen?
Sir.
Okay.
Yes, sir.
Okay, so as you can see, I'm going to talk about some problems in combinatorial commutative algebra and geometry. Now, this combinatorial commutative algebra is a relatively recent area which has evolved in maybe, I don't know, maybe in last 15 years, I would say, where it's a sort of in the crossroad of commutative algebra, combinatorics, algebraic geometry. So what my aim would be, as I have already mentioned, so let me also, this was the abstract of the talk which was shared with Pavel. So let me just say that we will discuss some problems related to numerical semigroup rings and their connection to geometry. So this numerical semigroups and numerical semigroup rings are sort of very standard objects in the field of commutative algebra and algebraic geometry, which hold a lot of combinatorial information, or rather I could say that it's a kind of a combinatorial representation of some geometric objects. And I will try to at least convey to you that how combinatorics connects to geometry and vice versa, and also what do we really mean by computation and computational approach to solving certain problems. Okay. So this is going to be sort of the plan of my talk, that I will slowly go through it, and I will just try to be as lucid as possible. But obviously, you can understand it's not very easy to do justice in a short span of time. And if you feel like you can even stop me when I'm lecturing, and I would be happy to answer your questions. Okay, so definitions and directions. So let us begin with field K of characteristic 0. For example, R or C. To be very honest, whenever you are doing algebraic geometry, most of the time the safest assumption on a field is that the field is algebraically closed. But here, the results which I'm going to talk about are mostly characteristic dependent, and most of these actually work even when the field is not algebraically closed. So that's quite interesting. But you can safely assume that the field is C, the field of complex numbers. There's no harm. But really speaking, we don't need that. Okay. Okay, so R will denote the polynomial ring in n variables over the field K. Now, you know, this is the famous Hilbert basis theorem we learn in the undergraduate classes, that if you take an ideal that is always finitely generated, ideal in the polynomial ring, it is always finitely generated. What does that mean? That means you get finitely many polynomials f1, f2, fn in I, such that every element of I can be written as g1, f1 plus g2, f2, and so on, gm, fn for some g1, g2, gm in R. Okay, and it is often convenient whenever you are saying something with respect to ideals in a ring, it naturally translates to the language of a module. And an ideal in a ring is a submodule of the module R over itself. Okay, so all these things you can actually say in terms of modules. And an R module M is said to be Noetherian if every submodule is finitely generated. So you all know this very basic definitions, which are sort of the pillars of basic algebra and commutative algebra. Okay. So the voice is not clear. Is it better now?
Sir, it is clear. It is absolutely audible.
Right, sir. Right.
Okay, no, I just got a message that your voice is not very
We
clear.
got it also, but I think it is very
It
clear.
is better now? Okay, okay. So maybe I'll hold this thing like this and then talk. Okay, so now, and I will try to talk louder. Okay, so finite generation of polynomial ideals is an important piece of information, no doubt about that, because you know there are rings, there are commutative rings where every ideal is not finitely generated. However, in order to carry out computations, one requires a good basis. Now you see I have put this word basis in boldface, but basis to be read as generating set, okay? So it is not necessarily a free generating set or a linearly independent generating set, just a generating set for an ideal so that the division algorithm produces unique remainder. We cannot answer the following question with any generating set. So you need a spatial generating set. And that question is what is very popularly known as the ideal membership problem. That if you have finitely many polynomials f1, f2, fm in R, don't forget R is your polynomial ring in n variables over a field K. Now, how does one decide whether or not f belongs to the ideal generated by the polynomials f1, f2, fm? Okay, so this is a very simple problem to state. You can understand that you take one polynomial f and finitely many polynomials f1, f2, fm, take the ideal generated by f1, f2, fm. Now you want to decide whether this polynomial f belongs to the ideal or not, right? Now, if your ring R happens to be a polynomial ring in one variable, then you have the beautiful division algorithm, right? We all know that if you have two polynomials f and g, and if g is not 0, then f can be written as q times g plus r, and that with the restriction of degree, etc., you have the uniqueness of r, and therefore, whether f is divisible by g or not is completely decided by the zero condition on the remainder. But unfortunately, the moment you move on to polynomial ring in two variables or higher, you do not have a natural division algorithm. Of course, I'm not completely correct in saying that. You do have, but point is, it is not a very straightforward generalization because for one variable, the degree of a polynomial works, but for several variables, the total degree is not the correct generalization. And therefore, you need a good analog of the division algorithm, and you have to do some work. You have to, the way it is achieved is through some monomial ordering, and then you can give a division process, etc., etc. But after all these, you still do not have the uniqueness of the remainder. So that is the problem. And therefore, whenever you are trying to answer this kind of a question, whether your polynomial f belongs to the ideal generated by f1, f2, fm, what does that mean? That means you should be able to write f as g1, f1 plus g2, f2 and so on up to gm, fm for some polynomials g1, g2, gm. Now, if you want to write that, you can, what do you expect? You would expect that the division process should yield the zero remainder. But you do not have uniqueness of remainder, and therefore it's difficult to answer. So now this good basis is that basis. So that means instead of just any f1, f2, fm, if you can choose a better generating set, so that better, of course, needs clarification, but unfortunately, I won't be able to go to that. But just let me tell you that that better generating set can give you actually uniqueness of remainder, and therefore it can give you a proper method, a good division algorithm where the remainder is unique, and therefore a proper algorithm to decide whether f is divisible by f1, f2, fm, or in other words, whether f belongs to the ideal generated by f1, f2, fm or not. So now this last part of this slide is very important. So this idea was implicit in Hilbert's work, and later on it became explicit, which is now known as the Grosvenor basis for an ideal. And you know that this plays a very, very important role. So whenever I'm saying that I want to do some computation, so what exactly I mean to say is that I'm trying to work on some effective method. I'm trying to actually construct a proof And there, I need a good division algorithm for the polynomial rings, okay? And it can be further extended. It can be even extended to local rings. You can talk about local order rings, etc. You can talk about standard basis and so on and so forth. But again, as I said, this talk will not allow me to go to that details. So the only statement that I want to make here is that, so the moment you have an ideal, even if you have some generating sets, because see, first of all, it's not very easy to find a generating set. And then I'm demanding more. I'm saying that I need good generating sets, namely a Grosvenor basis, so that the ideal membership problem can be solved easily, so that the implicitization problem can be solved easily, and so on. So you see, this is the computational challenge. Okay, so, and that's exactly what I will try to show you in some in this talk after some slides, that there are certain problems where possibly you do not have any other way out. So that is exactly what this talk intends to do. Okay. Now, a definition from commutative algebra, that a chain of prime ideals of length n in R is a strictly increasing sequence P0 contained in P1 and so on Pn, such that each Pi is a prime ideal in R. So you can see, by the way, I am not going to any ring other than the polynomial ring, at least for this talk. Actually, all these things can be sufficiently generalized to commutative ring with identity, which are Noetherian, even to local rings, etc. But for me, R is just a polynomial ring in n variables over a field K. Okay, and these P0 to Pn, you can see there are n plus 1 prime ideals, and you have a chain, and you have n containment. So this is what is called a chain of length n. Now, a prime ideal in a Noetherian ring R. So as I said, in fact, all these things can be very nicely defined in sufficiently general setup. But for me, R is just kx1, x2, xn. Sorry, there's a spelling mistake in Noetherian. So the height of a prime ideal is the maximum of the lengths n of the chains of the prime ideals contained in P. So imagine your Pn, and then that is contained in P. So you see how many such chains exist and what is the maximum length you can get. Then that maximum length is what is called the height of a prime ideal. And the Krull dimension of ring R is the supremum of lengths of all chain of prime ideals in R. Okay, so the actual definition is very, very geometric, but again, because of want of time and so on, I mean, I can't really get into that. So let us just take this, that this is the definition of height of a prime ideal and Krull dimension of a ring. Once again, ring for me is just kx1, x2, xn. Okay, so this is the supremum of lengths of all chain of prime ideals in R. Now, this theorem is a very, very important theorem for a commutative algebra, especially from the context of ideal generation, set theoretic complete intersection, and so on and so forth, or the kind of problems I'm going to talk about today. So this is called Krull's generalized principal ideal theorem. So what does it say? So again, a Noetherian ring is enough, but we are working on the polynomial ring only. Suppose I is a proper ideal in R generated by m elements. You know that every ideal is finitely generated. And suppose you know that I is generated by m elements, then you can say for sure that height of P is less than or equal to m for every prime divisor P of I. So what does that mean, prime divisor P of I? Actually, it means this, what you see in the next line, that prime ideal P containing I. Okay, and it is enough to take just the minimal primes. And if you look at those prime divisors containing I, then their heights are always less than or equal to the number of generators of I. So in particular, if your I itself is a prime ideal, then obviously what you can say is that the height of the ideal is less than or equal to the number of generators. Or in other words, the number of generators is at least the height of the ideal. Okay. Now, this is the starting point of a huge field of research, actually. So Krull's principal ideal theorem says that the number of generators you for a proper ideal in a Noetherian ring should be at least the height of the ideal. And what is the height of the ideal? And by the way, there's absolutely no harm if you just concentrate on a prime ideal instead of just any proper ideal, because what we will be discussing today are all a bunch of prime ideals. So take a prime ideal P in the polynomial ring K x1, x2, xn. Prime ideals are obviously proper. Now, what is height of the prime ideal? You see the definition here. So it is the maximum length of chain of prime ideals contained in that prime ideal P. Okay. And then it says that if you are trying to find a generating set for the prime ideal, then you need at least height P many generators. That's what it says. And now, what is further interesting, therefore, is that if you can define a minimal number of generators in a well-defined fashion, then that minimal number of generators has to be at least height of P. So that's exactly what Krug's generalized principal ideal theorem says. Okay. Now see, this gives rise to some really fantastic, non-trivial questions. And let me take you through this development, which is more than 100 years old. And you will see that how it has evolved and some my little contribution to these queries. Okay. So this is the main question. Historically, I'm not very sure if it was by Kronecker, because Kronecker's question was actually on set theoretic complete intersection. So the question was that in an affine space, if you take an algebraic variety of some dimension d, then whether it is cut out by the correct number of hypersurfaces. So that is what is called the set theoretic complete intersection problem. So this question is alive since, and Kronecker was the first one to ask, and it's alive from 19th century itself. It's the third quarter of the 19th century, and it is still open. Many people have worked on it. There are some developments, there are some results, but unfortunately there is no complete proof known yet. Okay. Now this question which I'm posing now is probably an upshot of that set theoretic complete intersection problem. But that's why I have asked whether it is Kronecker or not, instead of saying decisively that the main question is by Kronecker. So by the Hilbert basis theorem, every P, so this P is prime ideal, okay? So this Gothic P always denotes a prime ideal. So every P is always finitely generated because P is a prime ideal in the polynomial. Now by the Krug's theorem, each P needs at least n-1 generators. Okay, so why, sorry, I think I have missed one small, I'm very sorry. So actually what I meant to say is that, so suppose the height of the prime ideal is n-1. Actually, my prime ideal P will be the defining ideal of curves, and therefore they will be all one-dimensional prime, and that means the height is n-1. And remember, what is n? N is the number of variables in the polynomial ring, okay, which is also the embedding dimension for the curve. Okay, so we know that, therefore, we are assuming, I'm sorry, here I should have added that P is a prime ideal of height n-1. I missed that. So P, therefore, you need at least n-1 generators to generate P. Okay, so remember, n is fixed. Now your polynomial ring is K x1, x2, xn. That means it is a polynomial ring with n variables over the field K. N is fixed. And you have many prime ideals which have height n-1. Okay. And each prime ideal needs at least n-1 generators to be generated by. Okay. So a natural question is, for a fixed n, whether there is an upper bound on the number of elements in a minimal generating set for the ideal P. So therefore, you fix your n, you take all the prime ideals of height height n-1, then you know that you need at least n-1 generators to generate P. Now, is there an at most? given n, is there a function of n which is bounded function of n, and every prime ideal of height n minus 1 can be generated by that many elements? And the answer is no. So this is the main question. So here we are not talking about set theoretic generation, we are talking about ideal theoretic generation. Okay. So this is the main question, and my entire talk will be centered around this question, trying to give you the historical development and what kind of questions people ask and so on and so forth. Okay. Now, I said that P is a prime ideal of height n minus 1. So therefore, what it means is that it must represent a curve. So that is why I am coming to this, that rational parameterization of curves. So what is a rational parameterization of curves? So you don't see any curve here, I know. But the point is, in algebraic geometry, if you want to define a curve, then you have to define it through the coordinate ring, through what you call the normalization, etc., etc. Okay. So you have this map phi from kx1 x2 xn to kt. This is the map defined by phi x1 equal to g1t, phi x2 equal to g2t, and so on, phi xn equal to gnt. So what are g1, g2, gn? They are polynomials, non-zero polynomials, excuse me. Okay, we further assume that if you take this k g1, g2, gn, so that means you can understand that what is this k g1, g2, gn is going to be the image of this map phi, right? Which is going to be a subalgebra of this polynomial ring in one variable. So this is a polynomial ring in n variables, and you have one more polynomial ring in this extra variable t. A parameterization is a k-algebra homomorphism defined by this, and this is going to be the image inside kt. Okay, now take obviously this is an integral domain, so is this. And you take the field of fractions of k g1, g2, gn, assume that that field of fraction is exactly equal to k round bracket t. So I have actually simplified things so that I can straight away go into the definition of curve, and without getting into the complete nitty-gritties of defining a curve in an algebraic geometric way. This is perfect, and this way, so let me just quickly run through it. So phi defines a k-algebra homomorphism, and kernel of phi is p. That has to be a prime ideal, obviously. Now, and that the polynomial ring quotiented by the kernel is isomorphic to this is the image, and this has to have the Krull dimension 1, and height of p is therefore n minus 1. Okay, so I told you, right? This is a one-dimensional prime. So that means the Krull dimension of this ring is 1, and therefore the height of the prime ideal is n minus 1. Well, these are some basic facts of commutative algebra. Just accept it, and then we can easily understand the rest of the talk. Okay, so phi defines a rationally parameterized curve in the affine n space. Now this is an affine curve which is in the affine n space, and it is rationally parameterized. Well, it is in fact polynomially parameterized. If you, instead of polynomials, if you take rational functions and map it to k round bracket t, then it is rationally parameterized. But this is also, obviously, these are also rational functions. Okay, so this is a rationally parameterized curve in the affine space akn. And now this 4 and 5 are very important. Now, instead of polynomial ring, I have been saying that my R is always a polynomial ring. Well, yes, but at the same time, I would also be interested in this case, which is called the algebraic case. Okay, so this is often called the algebraic case, and this is called the algebraic case, where you are taking the formal power series ring in n variables over the field k, and this is also the formal power series ring, and you are taking the same parameterization. So you might as well take this g1, g2, gn as polynomials. There's no problem at all. Okay, and then here again, you can ask the same questions. So what I mean to say is that, just the question in the previous slide, that fix your n, you take height 1 prime ideals, I'm sorry, again, I'm making the same mistake. You take height n minus 1 prime ideals, then Krull's principal ideal theorem says that you need at least n minus 1 generators, but whether there is an at most when you fix the n, and the answer is no in general, and that is exactly what we are trying to investigate. Okay, so what I'm saying is here also you can ask the same question. It makes perfect sense. But interesting fact is that if you have answered this question here, that means for polynomial rings, that means the affine algebraic case. And then if you want to straight away migrate to this power series ring case, now that may not work because it has a lot more units, right, than this. And therefore, your irreducibility might break down. You may have reducibility that the curve that you are getting in the affine algebraic case may not actually work. Okay, so that requires some care. So you will see how people have done it, how people have taken care to that. Okay. Just a sort of a baby example that this is your well-known curve. This parabola is actually a nice rationally parameterized curve, and there are plenty of such, and we will see some of them. But why I chose parabola? Because this parameterize is what we are going to say a monomial parameterization, and these curves are what are known as monomial curves. And our talk will be mainly concentrating on monomial curves, and you will see that numerical semigroup rings actually very nicely fit into this monomial parameterization. Okay. Okay. Now here is the development. So possibly the question started with Kronecker, as I said, but I'm not absolutely certain, but definitely people started thinking about such questions. The first result came with Macaulay's, this is a seminal work, a very famous work by Macaulay in 1916, where he gave a family of prime ideals PR in the polynomial ring Kxyz. So it is in 3 variables which need at least R generators. So here itself, so therefore he is showing unboundedness because this mu PRs is at least R, and then this collection of all these mu PRs is obviously an unbounded set. Yes, R runs over the set of integers. Okay, I mean positive integers. Okay. So almost all the ideals define irreducible curves in AK3 with singularities at the origin, and these cannot be adapted directly in the power series rings. That's exactly what I said just now, that after Macaulay gave these examples, people tried to straight away take those examples in the power series ring, but unfortunately then it's that irreducibility fails, and therefore you do not have the correct example for power series ring. One requires some amount of effort. Okay, but interesting enough, then comes a very important, well, you might call it note by Professor Bankura, where it's called on Macaulay's example. It is published in the lecture note of Springer-Verlag. So this says that assuming that K is algebraically closed, he sort of rewrites the proof of Macaulay. But what is interesting is that, so he says that there are quite a few places where there's serious gaps, and that requires explanation. And he gives the proof, and that requires some very serious algebraic geometry. Okay, so what Macaulay's example was absolutely correct. There was nothing wrong. Of course, this work has several other things, but this particular example, it required more explanations, and then Bankura's work actually fills that gap. Okay, so this is a beautiful paper, and it's written by Avinash Sathe. Okay, and then comes, so you can see 1916 and then 1972. I do not know if there was any development in the meantime, but probably not. And then comes this work by Moe, who was Bankura's student, in 1974. And again, he writes another proof in 1979, where he gives a family of prime ideals PR in the power series ring. So you see here, it requires a separate work actually, which needs at least R generators. In fact, exactly R+1 generators. And these ideals define rational irreducible curves in AK3, which are analytically irreducible at the origin. But straightforward, just taking the Macaulay's example and putting them in the power series ring doesn't help. Okay, because as I said, it has lot many units, and therefore you do not have this analytically irreducible criteria. Okay, so this is a different example. I'll show you the example later on. So moreover, each PR is determinantal. So this is another very interesting stuff. So actually, I'm extremely interested in studying these varieties as well. So that's why I thought that it is worth mentioning here. And then almost around the same time came another very interesting example by Brzezinski. And here he gives an example in the polynomial ring, but in embedding dimension 4. So here it is in embedding dimension 3. Avankar explains it. Mo gives also in embedding dimension 3. Now Brzezinski gives in embedding dimension 4 and in the polynomial ring case. Okay. And here you can see perhaps these numbers do not make much sense to you, but and also it is not very clear how possibly Professor Brzezinski could have imagined these numbers. But towards the end of the talk, I'll be able to show you that there's a beautiful pattern, and that gives us a very nice generalization. You can say for sure that this class of curves always will have this unboundedness of generators. And but this work is very important, this Brzezinski's work. And here the statement, and this is the first example in embedding dimension 4. Okay, now here let us understand the problem well again. So what is our object of study? It's a prime ideal of height n-1 in the polynomial ring kx1 x2 xn and also in the power series ring kx1 x2 xn. And we are asking whether we can give a family of such prime ideals such that this collection of all these mu PRs or whatever you call it, the minimal number of generators for these family of prime ideals is unbounded above. Okay, and it is established that it is actually unbounded above, but all these examples look pretty ad hoc. So it is not very clear whether there is a bigger picture, whether there is a nice pattern which exists. And also this question I would say it is still open because I still do not have the complete proof. We are very close to giving a proof that in an arbitrary embedding dimension, can you give me a non-degenerate family of prime ideals of height n-1 such that this unboundedness is achieved? Okay, because see, the moment you have found it for lower dimensions, then you can treat the other variables as dummy and you can give that example. Yes, but I would not really say that. So there the curves actually is resting in dimension 3 or dimension 4, not exactly in the arbitrary dimension. So can one have a right generalization? So that's exactly what the question is. And some little contribution, this is joint work, so I should have mentioned at the beginning itself with my students Ranjana Mehta and Joydeep Saha. So what we have managed is that, so these Mohs curves, we kind of tried to understand, we revisited it, and Moh himself, in fact, if you remember this, Moh has 2 papers. 74, he first gives the example, and then 79, he again proves it, and the proof is in fact better, it has more information. And then we're trying to understand Mohs construction, and then we could give a complete algorithmic proof of Mohs theorem and a complete algorithmic approach which gives the complete generators explicitly for Mohs curves and shows that it is actually for that family you actually need an arbitrarily large number of generators. Okay. Now, as I told you that the examples looked pretty ad hoc, and we were trying to see a pattern, a bigger picture, and then another family similar to Brzezinski's examples has been created, which follows from a general construction of numerical semigroups. I'll talk about that a little later. And this and also you could see that this is an obvious question. So when you are talking about the minimal number of generators for an ideal, now if you're in a good setup, so what is a good setup? That means in a polynomial ring and the ideals are all graded, okay, with respect to standard gradation or with respect to weighted gradation, or if you are in a local ring setup. So there you do have Nakayama's lemma, and therefore you can talk about minimal number of generators. And then the minimal number of generators is actually the first Betti number. Okay, so what you are actually showing is that the first net Betti number, you have family of prime ideals and you have unboundedness of this family of the first Betti numbers. So obviously you can ask that what about the higher Betti numbers? And for Brzezinski's curve, we could show that, yes, it is all the Betti numbers have unbounded pattern. And in fact, the general model, which I will be giving you, for that also the same question is valid, but it is much, much harder to compute, much, much harder to show, because you know that any question related to syzygies, related to Betti numbers is extremely difficult to handle, extremely difficult. For low embedding dimensions, you can still take some computational approach and attempt. For arbitrary embedding dimensions, you do have some homological techniques, some like mapping, cone, etc. But you cannot say with assurance that it's going to work. Okay, it is really difficult. So that these are all questions which one can ask. And this is the ongoing work. I will come to that. That a non-degenerate family of affine curves equivalently dimension 1 prime ideals in the polynomial or power series ring in arbitrary embedding dimension, given by rational parametrization having an unbounded family of mu p's, that is being constructed. So as I said, why I am saying ongoing is because we have a family and it fits into the general model. We also know that what could be the generators, but you know, always finding a set of generators and proving that they generate is, you are back to that ideal membership problem. So it's not very easy. So that is exactly where we are very close, but I still can't say that we are done. Okay. Hoping that it would be done. Okay, so now let me quickly take you to this numerical semigroups and monomial curves. So this is where you will see the combinatorics part. So let me take you through some examples, because this algebraic geometric definitions and all, they are of course they're very it's not a 1 hour business. So let me instead take you through examples. So let's start with 2 integers m1 and m2. Let us say 3 and 5. Okay. Now what I have done is here, I actually intended to underline 3 and 5 as well. So this underlined 3 and 5 and the ones which are not underlined, obviously they're all the same integers. But what I meant to say is that this 3 and this 5, they are the integers m1 and m2, and this is the these are the coefficients, so that this the product they match. Okay, so this is just to distinguish so that you don't get confused. So you see, this is the most obvious relation between m1 and m2. That means what? 5m1 is equal to 3m2. Now suppose you raise it to the power and with a dummy variable t. Okay, so then t to the power m1 raised to 5 is equal to t to the power m2 raised to 3. Okay, now by an abuse of notation, if you allow me to write x for t to the power 3 and y for t to the power 5, then what you are getting is x to the power 5 equal to y to the power 3. Okay, so in other words, the relation 5.3 bar is equal to 3.5 bar gives rise to the polynomial relation x to the power 5 minus y to the power 3 equal to 0. You will understand in a minute why I am trying to show you all these things. Let me take you to another example. Okay. Okay. Before that, we should close this example. So you see, this x to the power 5 minus y to the power 3 is an obvious relation. So you don't really see x and y where they're coming from. I said that by an abuse of notation, let us forcefully introduce x and y. But you will see that we will have a very nice formal language to give this x equal to 2 to the power 3 and y equal to 2 to the power 5. Now you have this polynomial relation. Now the set of solutions of the above polynomial equation is actually a planar curve. Okay. Now moreover, the polynomial functions on the curve form a ring where the polynomial x to the power 5 minus y to the power 3 and all its polynomial multiples are 0. An obvious choice is therefore this ring. So this is what is called the coordinate ring of that planar curve. And what is important is that the ring A is isomorphic to the ring K T cube T5 because of this map. So now you see your that good old object is back where I was giving that rational parametrization. So in this case, this is the rational parametrization in 2 variables. And here you have KT and the parametrization instead of G1. So this is your G1 and this is your G2. Okay, and I told you, right, this monomial parametrization is very close to our heart, and we will be. That's why I gave you the example of parabola to begin with. And here you have one more. So this curve is actually defined by these numbers 3 and 5 through this parameterization. And why am I calling it a curve? Because the kernel of this map phi is actually a one-dimensional prime. And in this case, the height is also 1 because you are taking a polynomial ring in 2 variables. Okay. And in fact, you can, everything that I have written for 3 and 5, you can safely do it for any pair. I'm sorry, I didn't mean any pair, any co-prime pair of integers m1 and m2. The same thing can be done, and you will have x to the power m minus y to the power n. Okay. Next example. Now suppose I have 3 integers, 3, 4, and 5. Now, first thing is that what kind of relations do we have? Now again, I have tried to put them, this underlined ones are the m1, m2, m3. And these are some obvious relations. I have listed down 3, but of course you can write many more, because you can easily just multiply this by some integer and you can have plenty of them. But what is interesting is that perhaps I can call them the minimal relations. Okay, so these are the relations which sort of define all other relations. Once again, I am doing the same trick, that I am raising it to the power of t and I'm forcing some x, y, z. And then, so you can see the transition. Here you had integers. Here you were in the polynomial ring kt. Here you are in the polynomial ring kx, y, z. And you have actually three polynomial relations, or these are 3 hypersurfaces as we call it. And in fact, here you are saying that if we take the intersection of the loci of these 3 hypersurfaces, then what kind of geometric object do we get in the affine 3 space? If you just take this question as an independent question, it may look quite hard. But you see, in this case, you can very easily answer through this parameterization, because, well, not very easily, with a little effort, that if you take the parameterization from kx, y, z to kt, given by x going to t to the power 3, y going to t to the power 4, and z going to t to the power 5, you can show that the kernel is actually generated by these 3 polynomials, x cubed minus yz, y square minus xz, and z square minus xy. Okay, so you can show that with some little effort, and it is in fact a prime ideal of height 2, and therefore it actually defines a curve. Once again, a curve given by this monomial parameterization, t cube, t4, t5. Okay, good. So if we take the map, that's exactly what I said, that this is the monomial parameterization. Then is it true that the kernel of phi is the ideal this? Yes, with some effort you can show that. And in fact, this ideal is minimally generated by these 3 generators. And what is the kernel? The kernel is a height 2 ideal in this case. Okay, so you know that you definitely need at least 2 elements to generate. Well, here in fact 3. Okay, now you see just another way to describe this problem, that you can describe it as a map from this z3 to z, the set of integers, and this is the map given by phi of a1, a2, a3 equal to 3a1 plus 4a2 plus 5a3. I'm sorry, this should be a3. Yeah. Is it true that the kernel of phi is generated by the elements this, this, and this? Okay. So now probably you can see that you can go back and forth from the polynomial ring situation to the situation of these integers, and you are basically playing with these integer relations among 3, 4, and 5. What is the kernel? The kernel means phi of a1, a2, a3 is 0. That means, can you give me the list of a1, a2, a3 such that this is 0? Okay, and then not just the entire list, we are interested in finding some good generating set for that, for the kernel. Okay, finding that is equivalent to finding these polynomials. That's exactly what I'm trying to say. And here I would say that this is a more combinatorial question, or I don't know, maybe you may like to call it a more Diophantine equation question, and that connects to these polynomials and that connects to the curves. Okay, so that's exactly what I was trying to say. Okay. Another quick example, 4, 5, and 6, and I do the same thing here. But what is interesting here is that, so what is the difference between example 2 and example 3? In example 2, I had 3 such equations to define my curve. On the other hand, you can see that here the first and the third, they are the same. So you actually have 2 equations to define the curve. Now, well, there are enough reasons, there are enough explanations. Obviously, I'm not really, I cannot explain it now. It's not possible. It's requires some time. But this is exactly the case when you call that the curve is a complete intersection, and the previous one was not a complete intersection. Okay. So these are the bunch of geometric objects. These are the bunch of prime ideals P. So you understand what is the prime ideal. The prime ideal is the kernel of that parametrizing map phi. Okay, and we are trying to understand, we are trying to answer that question for a bunch of prime ideals, okay, which are defined by this kind of polynomial parametrization, in particular by monomial parametrization. Okay, and you will see that amazing things happen actually. Okay, so the above examples give rise to several naive but meaningful questions. So what are the relations among the integers, respectively polynomial equations, that describe all the relations among the integers, respectively polynomial equations? What kind of geometric object do we get out of these polynomial equations? What is the minimum number of such relations or equations? Is it well defined? And so on and so forth. Okay, so all these answers are very, very precise. They can be they can be understood, and commutative algebra answers these things in a very comprehensive fashion. And also, you can see there's a small flavor of computation associated to it. The moment you said that what are the relations, you are trying to actually write down, you're actually trying to list down the relations. And this is possible, of course it is possible, but with some amount of effort. So that is the computation that I was referring to. Okay. Now let me quickly just run through it. Pavel, may I know how much time do I have so that I can adjust my speed?
I think at least 15 minutes, okay. Around 15 minutes.
Around 15, thank you so much. Okay, okay, that should be enough. Okay, so now I'm coming to a general definition of a numerical semigroup. You start with n positive integers. Don't forget to assume that their GCD is 1. If not, then divide by the GCD and make them this GCD 1. And take all non-negative integer linear combination of these integers m1, m2, mn. Now, this is what we are calling, actually, we are taking a shortcut. This second paragraph should have appeared first, and then this should have come later. But I'm just sort of taking you straight there. So starting with m1, m2, mn, this is what we call a numerical semigroup. Well, justifiably so, because in general, a numerical semigroup is defined as a subset of n, and n includes, I mean n including 0, okay, so the non-negative integers, such that this is a monoid, that means with respect to addition, and then it is finitely complemented, that means n minus gamma is finite. So this is what is called a numerical semigroup. And it is indeed true that every numerical semigroup has a unique minimal generating set. All these things can be proved. These are some very, very fundamental facts about numerical semigroups. And by the way, numerical semigroups, again, historically, it is a little difficult to say how it came. But possibly, definitely in this context, the context which I am referring to, that definitely comes from the notion of value semigroups. And it comes from its association with curves. It comes from a very famous question of Oskar Zariski, and for understanding the nature of singularities. And then it was answered by Kuhn's, a question of Oskar Zariski. And then, that was sort of the beginning of 1970s when a huge amount of work has been done. And I'll show you from various perspectives. Okay, so this is numerical semigroup, and numerical semigroup always has a unique minimal generating set, and therefore there's no harm if you take this as a definition. And by the way, what I said, this GCD1 condition ensures that there exists an integer c. You see, it is finitely complemented. It should be finitely complemented, right? Now, how do you achieve this? That comes from the GCD1 condition. So you have one integer c such that which is in gamma, and c plus I belongs to gamma for all I in n, but c minus 1 is not in gamma. So one stage onwards, everything belongs to gamma, and that one which is not there, so this c is called the conductor of the semigroup, which is again a very important number, which gives you the which gives you a very important information about singularities and so on. Okay, so the semigroup is said to be symmetric if, so you take, so instead of this may look a little complicated, it's not really. So what you see that from 0 to C minus 1, remember, C is the least one in gamma, so that C onwards everything is in gamma. But before C, there are some integers which are in gamma, some which are not. For example, 0 is obviously always in gamma. Now, this 0 to C minus 1, you count how many are in gamma and how many are not in gamma. That number, if it matches, then it is called a symmetric semigroup. And this is a very important result of Professor Kuhn's, where he proved that was the result obtained from the question of Oscar Zaleski, that if you have a Gorenstein curve, then, or rather, if you have a Gorenstein singularity, then whether the value semigroup has some speciality or not. In fact, it turns out that it is a symmetric value semigroup for Gorenstein curve. That was the result of Kuhn's. Okay. Now here, I'm just back to that setup. I'm sort of rewriting that slide to you. So maybe I can just quickly take you to that slide once. Yeah, just a minute. Yeah, you remember? So this was my polynomial parametrization, that k phi of xi equal to git, and I assumed this. And then I said that the kernel is a prime ideal, and this is isomorphic to this, and the Krull dimension is 1, therefore height is n-1, and so on and so forth. Okay, and now I am taking my G1, G2, Gn to be very spatial, namely they are just t power some integer. So these are all monomials. They are not just arbitrary polynomials. Okay, so this is, yeah. So these are your G1, G2, Gn. Okay. Now again, the same thing is true, that you have this ring. This is the image of the map. This is isomorphic to this. This turns out that it is the Krull dimension is 1, which is very easy to see actually, because if you go to the ring of fractions and then this kt becomes actually integral over this. This is one dimensional, therefore. So etc. etc. And now this here comes a very important piece of information, that P is actually a binomial ideal. That kernel of phi, which is the defining ideal for the curve, is actually defined by such binomials such that there is A1, A2, AN and B1, B2, BN. You know what a binomial is, of course. There is a difference of monomials. And these exponents should satisfy this condition. Now you see, this is a very, very combinatorial or a kind of integer condition, right? So what kind of binomial should be there to generate P? This kind of binomial such that they satisfy this. So therefore, if you can actually list down all the relations among M1 to Mn, and if you can find the minimal ones, then you should be able to write the binomials. That's exactly what I was trying to show you in those examples. Okay. So and interesting enough, these elements, these are non-negative integer linear combination of M1 and 2Mn, and they are actually elements of the numerical semigroup gamma. So now you see this. So what is that you are interested in? You are trying to know how many generators are needed to generate P. Krull's theorem tells you that at least n-1 of them. But you know that there are families for which there is no upper bound. Now you know that you can actually search your generating set from this set of binomials. Okay, this is a very easy fact, by the way. I mean, you can easily prove this. But what kind of binomials? These kind of binomials with this condition. So therefore, the whole problem has now reduced to a kind of an arithmetic condition, if you allow me to say so, or a combinatorial condition. And you are basically trying to find out all possible relations among M1 and 2Mn. What kind of relations? Integer relations. Okay. So this is exactly what this combinatorial part is. Of course, there are other things. These are what are called the toric ideals and so on and so forth. But we are not going there. You can have a much more general setup. You can ask more general kind of questions. But at least you can see that there is the combinatorics, there is the polynomial ring, commutative algebra, there is the geometry associated. Because these prime ideals are very nice, they define very nice geometric objects. Okay, and by the way, these curves are very, very special curves that they are. By the way, they have singularity. They have singularity at the origin. Okay, so they're not smooth curves, and therefore that one singularity is posing all the problems. But it is still good. It has only one singularity. That is the the best part of it, actually. Okay, and the rest of it, you remember, I assume that K of G1, G2, GT, the round bracket K G1, G2, GT is KT, and in fact, it is indeed so because of GCD1 condition and so on and so forth. All these follow that the integral closure is this, Krull dimension is this. I guess here it is a slight typo, but anyway, you can understand. So this is a one-dimensional graded ring, and this is this is the coordinate ring of what we call an affine monomial curve, defined by this parametrization. Okay, so now this is the question that if you fix m, suppose that the integers m1, m2, mn generate a symmetric semigroup, is mu p bounded? Once again, it's an open question. No, there's very little partial answers known, and the main result that we know is only by Professor Brzezinski, and then there is some partial results here and there, but nothing substantial really. So this question is, so you know, symmetric semigroup I have already defined. You can take the parametrization, fix your n. Is it bounded? People think that it should be bounded, but it is not known. Okay. Now, these are some results about monomial curves. It really became a very interesting object of study in the 70s, starting with Herzog's work. This was in his thesis. And then gradually, many things happened, but mostly from the context of numerical semigroups. And then there was this periodicity conjecture about the periodicity of the Betti numbers. This was by Herzog, Huneke, and Srinivasan. And then myself with Philip Gimenez and Hema Srinivasan, we could answer that periodicity conjecture is true if the integers form an arithmetic progression. And then this Than Wu, he proved the conjecture in general in 2013. Okay. Now let me, these are about the good cases where you always have bounded kind of situation. Now let me get back to that unbounded kind of situation. So remember, Moe and Brzezinski, they were the most important examples after Macaulay. So this is Moe's example. Now you can see this Moe's example, the algebraic case in embedding dimension 3. And the example, by the way, this is not a monomial parametrization. You can see that X, that doesn't go to a monomial, but Y and Z go. Okay, so this, because the monomial parametrization in 3 space, that will not work. That will always give you the bounded picture. Okay, so it has to be a non-monomial parametrization. Now, in fact, Herzog's work proved that if you take the monomial parametrization for, and it is the polynomial setup, then it requires at most 3 generators. It is either 2 or 3. The 2 is the case when it is complete intersection. 3 is what is called almost complete intersection. Okay, so that is always bounded. So therefore, for embedding dimension 3, it has to be non-monomial, and this is Moe's example. Okay, and Moe in fact proves that mu pn. So you can see n is the parameter, and then this is the relationship between n and m, etc. And then he proves that mu pn is at least n plus 1. And he also proves, that was the work in the, he gave a hint that it is determinantal, makes it more precise in the second paper. And this for this family of curves, minimal number of generators is unbounded. And what we could, okay, maybe I should also mention this. So we, in fact, when we were trying to understand, we were first trying to understand the algebraic case. So that means what happens in the polynomial ring. You see, the polynomial ring is sitting inside the power series ring as a subalgebra. So suppose I just sort of take the contraction of that ideal in the polynomial ring, what happens? Okay, and then we saw that yes, for some cases it is in fact very nice. We have boundedness and so on, but still that does not throw much light on the unboundedness behavior in the power series ring. Now this again, how does computer algebra help us? So here you see your hands are tied. You do not know how to proceed forward. So in fact, if computer algebra was there at that time, probably all these results, whatever I'm going to tell you or whatever we are trying to do would have been managed very easily, I'm pretty sure, okay? Because otherwise it's pretty difficult. Sometimes you have to let me read out. So with the help of computations with, for example, this is a computer algebra software. You know, these are all free software. So we could study several examples to see an interesting pattern among the elements of the Grosvenor basis of Qn. If we write lambda in a specific way, so the way Amo wrote lambda, that doesn't help much. So if you take a lambda is right in a specific way, then it helps. And then it helps us to compute a Grosvenor basis and use the elimination theorem to construct a Grosvenor basis for Pn. Then a subfamily of Morse curve emerges from the computation. So what I'm trying to say is that, so here you have to see many examples, and some examples, these computing them by hand, trying to compute the generators by hand is an almost impossible task. So you actually rely on a computer algebra facility, and that helps you to develop some intuition. That's it, nothing more than that, but at least that's quite a lot. Okay. Oops, what happened? Yeah, okay. So this is what we could manage for Morse curve, that we actually finally we could write and we could give a proper algorithm to compute all the generators of Morse curve, and in fact we reproved Morse theorem. But I must admit that we reproved Morse theorem, but not completely independently. We also had to use some result in Morse paper. Okay, and so Mo wrote a very important lemma. And that helped us in finally writing, but it is a very comprehensive. You give me, if you give me any such parameterization, then we will be able to write the generating set for the defining ideal. Okay. Now, Brzezinski's example, this is the example which Brzezinski gave. I just wrote it in a slightly different way. There I used A, and here I'm just writing it as Q1, Q2. And here again, so let me quickly run through it. And here again, we could give a completely different proof. In fact, another family also. We could show that the Grosvenor basis exists for Brzezinski's curve. We reproved Brzezinski's result, and that actually helped us see that there is a very nice structure in Brzezinski's example, the way Brzezinski defines. Okay, so these integers, actually, let me tell you what the structure is. These integers, in fact, follow a very important, interesting pattern that if you sort of just rename them slightly, then what happens is the M1 plus M2, actually, it is not M1, M2. I think it is M1 plus M3 possibly. I just need to check once. Here, possibly it is, yeah. So sum of two of them is equal to the sum of other two. So that was the main point in Brzezinski's example, but sum of two of them is equal to the sum of other two, but they do not form an arithmetic progression. So that was the main thing in Brzezinski's example, and that gave us the general model. I'm coming to that. So anyway, so we could give a complete proof of Brzezinski's result in a different way, which I would say a more computational way. A complete Grosvenor basis was written, and that actually helped us see the moment you have Grosvenor basis, you have this Schreyer's theorem, which helps you write the syzygies, and then you have the other Betti numbers. And since here the embedding dimension is small, it's only 4, therefore you can comprehensively write all the Betti numbers, in fact, a minimal free resolution. Okay. Okay, so this second Betti number is at least this, and the third Betti number is at least this. So these are the results. Now this is the generalization, and I will quickly tell you what the generalization is and then stop. So a couple of minutes more maybe. Okay, so now here I'm just dropping that n and using e for the embedding dimension. Now you see what is the string of integers that we have taken. So we have taken an arithmetic progression of length r and another arithmetic progression of length s and put them one after the other, with the assumption that D does not divide B minus A. Which, how does it help? It helps because, so this is a string of integers such that you cannot complete it to an arithmetic sequence by throwing in some integers in between. Okay, and this is what we call the concatenation of two arithmetic sequences. Okay, and you have to assume that the sequence is minimal. That means no integer can be expressed in terms of the rest as non-linear, non-negative integer linear combination, so that to ensure the non-degeneracy. Okay, if this is called what we call the concatenation, so we have, and both the arithmetic sequences have the same common difference d, but the main criteria is here that d does not divide b minus a, so that if you throw in some more integers here, then you won't be able to fill it up with some integers and then make it a complete arithmetic sequence. Because if you can do that, then you have all sorts of boundedness and nice things happening. The moment you have disturbed the arithmetic condition, that is when you are likely to get unboundedness. Okay, but this turns out to be a very interesting family, and this is the general structure that we propose. I'm saying we propose because I still a little away from the proof that if you take these as the integers, by the way, these integers, these are degree 2 polynomials in n, okay, where n is just any integer greater than or equal to 5. So it is a very close imitation of Brzezinski, but not quite, okay. And then you have this string of integers m0 to me minus 1. You can see that here you have m0 to me minus 3 and then the last two. So this is the concatenation, and then you can actually show that if your embedding dimension is restricted to 4, then you have another class where it is unbounded, and that is it is something like Brzezinski but not quite. And here is the conjecture that this family is actually unbounded for arbitrary embedding dimension. Now this is what I said, that this is the ongoing work. Okay, so I will end with this. Some other directions of research, and with this monomial curves, with this numerical semigroup rings, you have all sorts of questions you can ask. At least these are some areas where I have tried to understand, I have tried to work, and there are several more. But so these are many directions in which people are interested. So this is from the very ideal theoretic questions on Grosvenor basis, syzygies, the computational aspects, then the questions on syzygies and Betti numbers, derivation modules, again the singularity study, smoothness of blow-ups and transverse conjecture. This is another very interesting conjecture, which I could prove only for some special cases. This is still open. This is about again related to singularities, set theoretic complete intersection conjecture, which is still a very important open problem. And then projective monomial curves is another study. And the coin exchange problem, this is purely from Diophantine equations number theory. Okay, so this is a very recent this paper. I mean, I wrote it long back, but very recently it has been posted to arXiv. You may like to have a look at this. So this is like a survey article where I have listed down some open questions which people are interested in, or at least I have worked on. Okay, some references. So this is that famous book of Professor Macaulay and F.S. Macaulay. Then this is Avankar's comments on that, etc. And this book is very useful, Kunz's book. So thank you. With this, I end my talk.
Thanks a lot, sir. Thank you very much for your remarkable speech. Like always, it is a pleasure to listen to you. Actually, you always cook very tasty, spicy dishes in a very casual way. The possible questions coming to our mind has mostly already been explained by you, but there are some questions I have already put in the chat box. Can you, sir, please see the chat box?
Yes. So I see that
the first one is given by Monojit.
How can we prove generators are minimal?
It is from actually your
examples,
from page number.
I can see those questions. So how can we prove generators are minimal? Well, if you are lucky enough to have generators, then what usually people do is that you can localize with respect to the maximal ideal and make it a kind of a vector space setup, and then reduce the problem to that of a linear independence problem and check that they are minimal. But believe me, these problems are, I described it in as Pavel says, that very casually, but these problems are often very challenging. It's not very easy to always check or prove that they are minimal. But if you have a minimal, if you have a generating set, then you still at least have some hope to prove minimality. But it is not easy. It is not easy because, for example, the conjecture that I showed there, we do have a generating set, and we are almost certain that this is going to be a generating set. But proving that it is exactly a minimal generating set is exactly where we are stuck at the moment. If we can prove, then we are through. Okay, so and it's very, very difficult to say really what is a kind of a good algorithmic process, except for some ad hoc treatments. Okay, so I guess this is a question from Professor MEAKIN, that is it true that the ideal membership problem for every Noetherian ring is decidable, or might it be undecidable? Well, very frankly speaking, Professor MEAKIN, I can understand the spirit in which you are asking this question, Paraj, but I do not really know. See, the question is for every Noetherian ring whether it is decidable. That's probably quite a big thing to expect, because question is how do you first have a reasonable term order, and whether you have the right analog of a standard basis or things like that. So this, frankly speaking, I do not know whether probably it's more of a kind of a person working in computer algebra probably can answer your question, but I really do not know. But yes, of course, for polynomials and power series ring, we do have answers that your Grosvenor basis techniques or standard basis techniques do work. Yeah, or even I can say perhaps for good local rings. Have I answered your question? I don't know, or if you do you have?
Thank you. I just wasn't sure of the status of this. So it's
Right.
clear for
Yeah.
then, right?
But
I would expect this to be very difficult.
Yeah, absolutely, because you can have with various kind of complexities. You know, this is, I do not know really what kind of challenges people would expect. Yeah.
But the polynomial rings, it's true. Yeah.
Yes, of course. Yes. In fact, that is what is giving us all the hope to work on such problems, really. And that if you can have a reasonable Grosvenor basis, well, knowing a Grosvenor basis is a big deal. Most of the time, we do not have that even. So we have to be satisfied with the basis, because if I know a Grosvenor basis, as I told you, that for Brzezinski's examples, we could actually compute a Grosvenor basis. Brzezinski did not really find a Grosvenor basis. Brzezinski just found a generating set, and he could prove that it is minimal. Okay, and exactly the way I answered Monojit's question, how that you localize with respect to the maximal ideal x1, x2, xn, and then you just prove linear independence, sort of. But point is, finding a Grosvenor basis, probably he didn't even bother to look at that. That was also a possibility, because Grosvenor basis became formal possibly after Brzezinski's work, because it was made formal in Buchberger's thesis. Okay, so that was probably 1975, if I'm not mistaken. Okay, so but the moment Grosvenor basis was formally defined, and then and then Schreyer's theorem connects it to computing the syzygies, the syzygy tuples. That's kind of a very important bridge. And the moment you have that, then you not only know the generators, you know the relations among the generators, and you hope to see the syzygies.
Mm-hmm.
But since it is small embedding dimension, it could actually tell us what the higher syzygies would be. So finding a Grosvenor basis is the main hope we sort of depend on, and that is decidable for the polynomial rings.
Yeah. Okay, thank you.
Thank you so much. Okay, sir, can we find Grosvenor basis for Qn by Buchberger's algorithm? So by Qn, probably you mean in Mo's example. Yes, that's exactly what we did when we contracted it to the polynomial ring. Yes, you can find. And with some amount of effort, we did that. So QN is the contraction of the ideal PN, and that is there in that paper. But unfortunately, we thought that we would be able to find a mechanism to take the ideal PN, contract it to the polynomial ring, know the Grosvenor basis, and then, lift it up. But that transition is not always very easy. I mean, you can contract, yes, and we do have a Grosvenor basis, but unfortunately, there is no way to go back to the power series ring because you pay a price. You have lots of units there. So you do not really get back your ideal. That's the problem. You still get something smaller than your original ideal. So it helps. It is, but the contracted ideal in the polynomial ring is also very interesting, by the way. It's a nice object to study. So one can even take this kind of parametrization, which is a non-monomial parametrization in the polynomial ring and study. And that study hasn't happened at all. But that's hard. That's really hard because your ideal, the defining ideal, is not going to be a binomial ideal. And therefore, it is even binomial ideals are hard. The binomial prime ideals there's what are called the toric ideals. They are also very hard, but still you have some combinatorial representation and you hope to get some nice results. But if you do not have a non-monomial parametrization, then it is a very difficult question to answer in general.
Thank you, sir. Thank you. So I think all of the questions that we got are answered.
So can I stop presenting now? Yeah.
Yes, sir.
Okay.
And thank you again for this nice, wonderful session we had. Now I hand over this session to Dr. Bappa Das. Can you please, Bappa Das?
Perfect. So thank you very much to our respected speakers, Dr. John MEAKIN, Professor ABHIJIT DASGUPTA, Professor A.P. Singh, and Dr. INDRANATH SENGUPTA, and all of our dignitaries, participants, colleagues, and students, as well as scholars. Thanks a lot. Since we cannot avoid the limitations set by time, so we have to end this session right now. Now, on behalf of organizing committee of this international conference, a 2-day international webinar on algebra analysis and topology, I would like to request Dr. Ajay Mukherjee, head of our department, Bankura University, to deliver the vote of thanks and conclude the session. Actually, Dr. Ajay Mukherjee, please continue.
Okay. Thank you, Dr. Das. Our today's webinar is almost at the end. Here we are just give the thanks of vote on behalf of organizing committee. We, the members of organizing committee, are immensely grateful to the honorable speakers. Their prompt and spontaneous interaction with the conveners has helped us the most to overcome the barriers of different time zones and different work schedules. Despite their busy schedules, they are kind enough to spend some time with us. We are very much thankful to all of you, speakers. Thank you very much to all of you. We would also like to express our sincere gratitude to our Honorable Vice Chancellor and Registrar for giving us the best possible support from their sides. Professor D.K. Ganguly, retired professor of Calcutta University, and Professor S.K. Sardar, Jadavpur University, have enriched this webinar by joining here. It is due to Professor Ganguly we have got Professor Singh in this webinar. We extend our thanks to them. Dr. Rajlakshmi Mukherjee, Assistant Professor in Mathematics, Garbetta College, has also immensely helped us to make the event grand success. We are really grateful to her. Let me also thank all the participants for showing interest and being with us throughout the program and listening the lectures patiently. We are also thankful to our respected faculty members and the members of Bankura Mathematical Society. And last but not the least, we are also thankful to our beloved students for their active participation and cooperation. Hope we will meet again very soon. Please be safe and careful. Thank you very much to all. Thank you. Thank you.